my little children in honors chem, they need somebody to adopt them, and they are doing this right now. So you can do your good people points and review at the same time. Okay, so if you want to adopt them, I'll give you their numbers. No, I don't have their numbers, but I'll tell you where they live. Okay, so anyway, percent abundance is basically of all the isotopes in the world, of all the oxygen atoms you could go pull together into a big bowl, you're going to find 99% of them, and this is approximately the correct numbers, I don't have the exact stats on this, approximately 99% of them are going to weigh 16 AMUs, atomic mass units, right? Atomic mass units we use interchangeably with grams due to the fact that we don't work with AMUs very well. We can't mass them, so we always relate grams and AMUs because they are directly related. Anyway, 99% of them is going to weigh 16. What makes up that 16 mass? What two parts of the subatomic particles? Protons and neutrons. Electrons essentially are massless, right? 0.5% is each going to weigh 17 grams and 18 grams based on the isotope. So who is wrong in this case? Dalton. Dalton said with the atomic model or atomic theory that every element or every atom of that particular type of element was exactly the same because they had the same properties, right? Mostly true. They have the same properties, chemical properties, physical properties, but they are not the same because you can have isotopes or varieties or versions of every single atom out in the world. So to find the average atomic mass, which is the mass that's published on the periodic table, because oxygen is really close to 16 at 16.00, but like cobalt, 58.93, you will not find a cobalt atom that weighs 58.93. It's a lie. That's an average of all the cobalts in the world. So the periodic table gives you one number that represents an average. We can actually establish different masses for different isotopes that would be very specific to the isotope. So the way you calculate the average atomic mass, which should be, average atomic mass is what that stands for, which should be what's published in the periodic table, is going to be this way. You take the mass given to you, and I'm going to put AMUs here, but you can say grams, it's fine. 16 AMUs is what that isotope of oxygen weighs. 99% of the total is its relative abundance, so it's abundance in general. But you can't multiply this by 99 because that's going to be like 160 something almost, and that's way too much. So you have to multiply by the decimal version of the percentage. So divide by 100, 0.99. You'd also do the same thing for these other two. So 17 AMUs, 18 AMUs for these two other isotopes, and then what's their decimal percent? What's their percentage as a decimal? 0.005, because you move the decimal back 2, right? And then 0.005. Add that up. Once you do this times this times this, all you do is add it up. It's not a normal average. You do not divide by 3 in the end, okay? No division in the end. You've already counted for that percentage or that abundance in your percentages. So do not try to do anything else sneaky. Just add it up. You should get, this is not going to be right because I made these numbers up, 16 AMUs, and that's what should be published in the periodic table. So you could do this for anything. I could give you 5 isotopes. You'd have 5 masses and 5 percentages, multiply them, add them, done. That's how you get an average atomic mass. Thumbs up if you get here. Okay. Also in the reading you saw this Coulomb's law. I think we have talked about this before. We have, okay. I swear, sometimes I can't remember what I talked about in this class, in last year's class, in my honors class, okay? So, this is called Coulomb's law. So you know who Coulomb is, because we dealt with the Coulombs, the charge of the electron, in electrochemistry. So with this one, it's one of the most useful formulas in chemistry and physics, because it helps you determine the force of attraction or repulsion. So this force can be an attractive force or a repulsive force, okay? And that's just basically the two charges of anything. These two things can be protons and electrons. They can be cations and anions. This one I use all the time for cations and anions. Cation and anion. It can be electron and electron. It can be proton and proton. It can be anything that has a charge. Obviously, if they're opposite in charge, they're going to attract, so we're calculating the force of attraction. And if they're the same charges, like an electron and an electron, they would be the forces of a repulsion. But regardless, all you do is whatever the charge is, you're plugging in for Q. So Q is representing charges here, dividing it by the distance in which they are separated by. So the best example of this one would be for a nucleus. Energy level 1, n equals 1 is an energy level, right? So the first energy level of any atom, the electron is really close to the nucleus, right? So the distance is small, so the attractive force, small denominator, yields what for force? Larger, right? But if I go out further, and this is going to be kind of like a Bohr model image here, if I go out further, and I'm out here at n equals 2, this electron is farther away from its nucleus, so therefore the force what? Decreases. The attractive forces decreases. So you know that as logic, but there's a mathematical explanation. So I'm going to try to throw the math back in when I can, because we're in very qualitative chemistry right now. So those of you math lovers out there, bear with me. So we have a lot of more talking, explanation, and reading, justification, stuff like that in this unit. Okay, so that's called Coulomb's law. It's used for really the explanation for most attractive or repulsive forces that we will ever talk about. Okay, atomic theory. This stuff is what Dalton proposed. I'm going to tell you his false stuff. Okay, you will read some more about Dalton if you wish. I think it's chapter 2 and 7 in your book, but you can find it, okay? So the history of the model, I'm not going to go into extreme detail about, because I do not like teaching about the history of the model of the atom. I like to talk about the stuff they got wrong and their progress from that. So he said that all atoms of the same element were the same. Lies. What do we now know? There's what? They're different because they are called isotopes. So we know isotopes exist. He said atoms are indestructible. You cannot tear them apart. Can we? Yeah, it's called nuclear decay. So you definitely can. He said they're indestructible. So I still say yes, somewhat they are still indestructible. But we can pull electrons out. You can remove electrons. You can do nuclear decay. Oh, and while I'm thinking about nuclear decay, so in semester 1 you had an organic independent study. You have a second one in semester 2, which I wasn't going to tell you until after we got here, because now it's relevant. It's nuclear chemistry. It's much shorter. I feel it's much shorter. And I have some nice, cool Hulk images in there, because gamma radiation and nuclear decay. So you'll have some review with that, but then you'll actually find out some really, really cool things about why certain atoms decay and why some don't. Or why is uranium and plutonium used as the nuclear cores in nuclear chemistry engineering and in nuclear power plants, versus potassium or chlorine. So that one, it's not due till the day before the test. Okay, your test is a month out, March the 11th. Okay, so a month from today. All right. So anyway, I'll show you that is on my website as well. Okay. Oh, and then the last thing that's now a falsehood is that he said any given compound of 2 elements, so like let's say hydrogen and oxygen, they always occur in the same ratio. Lies. We say hydrogen and oxygen can occur in a 2-to-1 ratio or 2-to-2 ratio, right? So now the same fixed numerical ratios what Al Dalton proposed, he got us started. We were like, no, look, these things weigh different, and they have the same math, or they have the same elements in it. So this is called the law of multiple proportions. And that makes a lot of sense, because now we say, no, there's not just one proportion they can exist in, there's 2 proportions they can exist in. So it's almost, like we're just trying to point out some of their wrongs. But we use it to walk through the evolution of the model, of the atomic model. All right, so here's the law of multiple proportions in more detail. You can read this on your time, but whenever the 2 elements form more than one compound, the different masses combine with the same mass of the other element in a ratio of small whole numbers. It just means you can have different subscripts. And then we go through an example here. Sulfur dioxide to sulfur trioxide. Their masses are different due to their number of oxygens that differ. And so they sometimes will give you data and say what law is this describing. If it's just a different ratio of the atoms, it's just the law of multiple proportions. So that's all based off of Dalton's first proposal of the atomic theory. So that was what, 200 years ago, right? 210 years ago. It's not that long ago. I mean, I don't think, but maybe it was. Okay, so that's what his atom looked like. Very plain. J.J. Thomson came and did an experiment with a cathode ray tube, and what he discovered was that whenever there's a beam of particles traveling through a tube, you held a magnet to it. That had a negative end. The ray that was going through the tube would deflect downward. So the south end of the magnet, which is the negative pole, was doing what to the matter? repelling it because the matter was what charged? Negatively charged. So he discovered the electron. And so what he thought though was that matter, this general atom shape right here, matter just had these little spots of electrons just randomly in there. And he said, so the rest of it must be positive, because he did the second experiment where he held the magnet up again, where the north end was pointed towards the gas, and it obviously attracted it. So he said, okay, there's positives and negatives stuff in matter, but I don't know how they're arranged. So I'm going to propose this model called the plum pudding model. Good. And plum pudding was like pudding with raisins in it that they ate in England. So that's what he's like, yeah, it looks like that. So that's J.J. Thomson. And then Rutherford was like, good job, J.J., let me see what I can do here. So he continued the research. He started doing something with gold foil. Remember the gold foil experiment? The gold foil experiment was one where he had a ray of alpha particles, and the ray of alpha particles, alpha particles are a helium nucleus. This is what an alpha particle is. It's a helium nucleus. Alpha particles, that's what it's labeled as. It's like a fish. So he shot the alpha particles at this gold foil, expecting them to go straight through because there was not a whole lot of mass that seemed to be in the atom. Thought they would go straight through, but what happened was there was a large angle of bounce back, deflection. Is that the word I'm looking for? Okay. So they bounced right back at him. He was like, oh my gosh, what's happening? Something's in the middle of this atom. So he was like, oh, hard, dense core in the middle. Let's call that the nucleus. And he went on further and did some more experimentation to say that the nucleus was the hard, dense core and also had a positive charge to it. So then he said, okay, I think the electrons exist out here, but I know for sure there's a dense hardcore nucleus. So that's Tom Rutherford. Yeah, but what's Rutherford's first name? Ernest Rutherford. Thank you. So we're 100 years into the atomic model now. Now let's finish it up. After we got the whole nucleus discovered, there was some more experimentation. I did miss Chadwick. Chadwick was in between. After Thomson. That was Millikan, I lied. I think there's two L's. Millikan. Millikan did a follow-up experiment from J.J. Thomson that was called the oil drop experiment. Oil drop. And what he did was he had oil. He shined X-rays on the oil to give them some energy, and he quantized that energy to figure out how much energy that oil had. And he said it was always in specific multiples, and those multiples meant there's a certain number of electrons with a certain charge in the stuff we call matter. So that helped JJ's cause, because JJ was like, yeah, there's electrons in there. I think they're in a ratio, but I don't know the ratio in which they exist. Millikan went further and was like, aha, I now know the charge of an electron, which is like, 1.93 times 10 to the negative 19th coulombs, something like that. I can't remember off the top of my head. But he found the actual charge of the electron. Sorry. Then Rutherford said, okay, there's a hard dense core nucleus. And then we just said there's some positive stuff in the nucleus. After he came, Chadwick did some experimentation to say, okay, I like Rutherford's model, but I think there's something else in there, because if all those positives were together, positives repel as well. The nucleus would essentially explode because they would be repelling each other because they're just laying on top of each other. So I think there's something in the middle there that we're not thinking about. So he discovered the neutron. So the neutron allows for the protons to sit near each other, but they're Switzerland. They sit in the middle so that they can't fight, pretty much. So he discovered that there's that mass that we were accounting for, but the charge wasn't there. The mass is accounted for because there's neutrons in there that are neutral, but don't apply to the charge of the individual, of the nucleus. So that's the last one, is for just the nucleus and our relation, is Chadwick. Then Niels Bohr comes into the picture, and he said, okay, I think these electrons we've been talking about, we know the charge, we know that they're there, but how are they arranged? He started to say they were arranged in energy levels or orbits. Orbits, not orbitals, orbits. It seems like it's the same thing, it's not though. Orbits are circular, as noted here, and they have the electrons had set paths that they could travel. And that's pretty much all he knew. And everybody very much applauded him. They were like, oh my gosh, great, we've solved the puzzle of the atom. But then after that, they started to realize that they tried to run Niels Bohr's like experiment on some other matter. It didn't work for anything other than hydrogen. So his calculations were very good for hydrogen, but it's one electron. I mean, how much you got to keep track of here, right? So he worked with hydrogen very well. The Bohr model did not work with any other element. So Schrodinger, Einstein, Schrodinger, yes, Schrodinger's cat didn't die, or did it? Right? So that was a thought experiment. No animals were harmed in that experiment. Okay. So Schrodinger, Einstein, Heisenberg, Planck, de Broglie. I think there's probably a bunch of other people too. These are all kind of the quantum physicists and chemists. Bunch of people, okay? They helped create the new modern model that we currently support. I don't like to say believe in or, because we don't believe in science, we support science. The evidence supports its theories. So they all come up with a quantum model that we're going to talk about more today, where the electrons are not in set paths. I don't know if you can see these. These are dots. You see the dots? Those are called electron clouds. They're clouds where electrons possibly could exist. But we know, in general, we have a high probability of finding the electrons in an electron cloud. We're not going to say they're exactly there at this angle, at this speed, tomorrow, okay? We're not going to know extreme information, like, we're not going to have a lockdown on these electrons. We're going to know the general information about the electrons. They're in this area. These clouds look like they're rings. That's because this is a really cheesy model of it. The clouds are not in rings. The clouds are multiple different shapes. And those are the SPDF shapes. Oh, this is another, that's not it. S is a shape that's a sphere. P is a shape that's a dumbbell. You remember SPDF and electron configurations. Okay. The electron configurations probably seem like a bunch of numbers and letters to you. The electron configurations are saying in which cloud they live in, which neighborhood the electron lives in the atom. It's telling you the configuration of the electrons around the nucleus. Are they on the first level or are they on the second level? Are they in the S spherical shape or are they in the P dumbbell shape? It's giving you a lot of information about where the electron lives. And the P orbitals, they look like this, but they come in three. They come in the y-axis version, the x-axis version, and then the z-axis version. Z is supposed to be looking like it's going into the board and out of the board. You see it? Am I drawing this? That's okay. So this is the z-axis version. So S is just a sphere. The spheres can get larger as you go up in energy levels. They are small in the equals 1, larger and larger and larger as you go up. P's can also get bigger. These are all P orbitals. They all come in. If you get one of them, you get all of them. It's one or nothing. You can't choose which one you want. They're always there because you can always shove electrons in them. The D ones I cannot draw, but I will draw as best I can. So this is S, this is P. D's are double dumbbells. Okay? And I cannot draw that in all the different orientations that they partake in because it's ridiculous. This is in the X and Y axis. But then assume there's another one in the X and Z axis and the Y and Z axis and then the X squared Y squared axis and then like the X squared ZY, that axis. So I don't know how to draw those, but I will show you pictures of them. All right, so the D's have more room because that's those transition metals, right? D block is transition metals, and that's got so many more electrons to work with. So that's what we kind of, as we get higher in electron count, we have to make more room for them, more neighborhoods. And then as you go one more step further to F block, F block's the lowest part of the periodic table, they have a flower appearance. There we go, flower appearance, okay? So F is a flower appearance. That looks like P, that's an F. I just draw my F spheres. Okay, so this is how much we have evolved the atom. From a single sphere to all of these different orbitals, I didn't say that earlier, Schrodinger was like, no, I'm not going to say, I like the word orbit, Laura, you did a good job with orbit, but I'm going to call these orbitals. Orbitals are different than orbits. So these are all the different shapes of the orbitals. Cool? If you get bored and you need to stand up, by all means do it. This is why I'm going quickly through this because this can become very tedious sometimes. I'll try to give you some good, exciting news. Okay. I highlighted the things that are kind of new or more important. Let's go back to subatomic and then we'll come back to the quantum model. We know that protons never change. Proton number is called Z number. I don't know if you've ever heard that, but the Z number, we will refer to the Z number as the proton number all the time. It's also the atomic number because the proton number is the atomic number because they're the same thing. The mass number is the Z number. The only reason you need to know this is because you need to know what A to Z notation is. Okay, so if I give you an element and I write it out with the top and bottom number, this is called A to Z notation. Yeah. Okay. No, I'm sorry. The A number is the mass number. How did I never know that?
No, because it says if neutrons is equal to
Oh, mass minus. Thank you. Because I was like, what did I do? Thank you. This mass number is the A number, though, so I do want you to know that. Mass number is A number. Thank you, both of you. Okay, so this is called the A to Z notation, and this is how you denote isotopes to be specific masses and specific element. So if I wanted you to write the A to Z notation of sodium, the most common isotope of sodium is going to be whatever the one that's closest to the average on the periodic table. Sodium was 23 or 22.99 is the average. So I'm going to say the closest isotope would be 23. The atomic number of sodium is 11. There you go. A to Z notation. How do you figure out how many neutrons you have? Subtract. I love A to Z notation because I can subtract. 23 minus 11, 12. I love it because it's like a little math problem set in itself. And then, purpose of the nucleus, they sometimes like to use this term. The nucleus helps the proton stay together with strong force. It's just there to limit repulsion, really. And then you know that if I get a cation, I've lost an electron, and if I have an anion, I've gained an electron. Okay. Anion, gain electron. Okay. A to Z notation. Good. Oh, here's my mass right here. So A to Z notation, you can have an isotope denoted that way. There's a charge, obviously, noted. And then mass, you know that if I give you like uranium-238, 238 is the mass. Yes, yes? Give me some feedback, people. Okay. I just need to make sure I'm just trying to hit the highlights here. Okay, how in the world do we figure out this crap? We figured it out because we have a mass spectrometer. This is what we learned in Unit 1. Mass spectrometers have this nice, going this way, yeah. Nice way where they can actually be, you can put some gaseous ions or gases in here, period, and they'll run through a magnetic field, but when they get to the magnet, the ones that are really, really light, when they're deflected, they deflect because they're lightweight, right? The ones that are heavier deflect a little less. So what happens is as they deflect, you can see the path between here, and then the ones here deflect the most, and the ones that are heaviest, they're hard to move, so they deflect less, so they're going to stay straighter. So if you had to point out, you would say the ones up at the top of the detection plate are the lighter ones, less weight, smaller mass isotopes, and the ones at the bottom of this detector plate are the heavier ones. And that's how they separate isotopes. If you have one big sample of all the oxygens in the world and you want to separate them out, the oxygen 16s would hit up here, and the oxygen 18s would hit down here, and then in the middle would be the oxygen 17s. And what they do is they count the number of hits at the detection plate, and that helps you get the relative abundance. Yeah.
If you say it was heavier and they don't move as much, wouldn't it hit straight in the middle?
This picture is pointed towards you.
Okay.
And the detection plate is actually higher.
Okay.
But they don't move as much because there's none of them that are going to deflect the other way. Because they're all the same sample, so they're all going to deflect in the same direction, but they're going to deflect more or less. Okay. I have a video too, but I'm not going to show the video right now. But this picture just is kind of weird. Okay. Wow! Fun fact. What was my fun fact? Oh. Electrons are incredibly small. A single speck of dust has more electrons than the number of people who've ever lived on this earth.
Whoa.
Are you actually amazed, or are you
Yeah,
just
I
playing?
actually am.
Every time I read that, I'm amazed. And I've done this like 5 times. Come on, that's insane. More electrons than people who've lived on this earth. Again, thank you. Like, I am so amazed by science, I might cry. Okay, so the main reason I want you to hear that is because we're focusing on the electrons at this point. Who cares about the protons? That's all about the nuclear chemistry you're going to be reading about. The electrons are what we care about because they create the chemical reactivity of everything. If something has a really strong hold on its electrons, ain't nobody going to touch that. It's going to stay there by itself, a lonely old maid with cats, okay? Nobody's going to touch that. But if it has electrons that are free to go about and play, they're going to be really reactive. So I personify this a lot, but basically we're talking about things that are able to give up electrons or things that are able to receive electrons and their ability to exchange them between. So we're talking about everything. Every chemical reaction out there is only dependent upon the electrons, and that's it. So we need to directly figure out, can we observe the electrons? Well, no, you can't directly observe the electrons because electrons are really finicky. And if you even shine light on them, electrons get really excited and they start to do stuff they didn't do before you observe them. Does that make sense? So even if you try to look at an electron and try to observe something about it, you're going to change its behavior because you've done something to it to make it visible to you. The only way we have visibility is because light bounces back and hits our eyes, right? So what's it going to hit when I look at it? The electron, right? So here's what we talk about at honors time today, and I just left on the board for you guys. What happens is when I'm going to start on this side. Whenever you have photons, light, right? Quantum particles, packets of light. These photons have energy associated with them because they are part of the electromagnetic spectrum. EMS, electromagnetic spectrum, which is a really long wave thing, and then you get really tiny waves. Okay, it's just straight up energy. As the energy from these photons are directed towards the atoms or any matter period, the electrons in the matter can absorb that energy. And when electrons absorb the energy, this is an electron in M equals 1, by the way, this electron jumps up for joy, and it goes out to the outer energy level. It's like on a sugar high. It can only stay there for so long, and then it's going to crash. We've all had the sugar crash or caffeine crash. Okay, as the electron has the sugar crash, and I'm going to kind of draw this again as an open hole so it looks different. As it crashes, back down to ground state. This is excited state. This is ground state. This is all familiar, right? Mm-hmm. Okay. As it crashes, it's going to release that extra energy it just gained. And the way you can see that here, if the energy is released, there's light put off, or some sort of energy put off with a special wavelength. And what we can see, because we can literally see that energy put off, if it is in that narrow spectrum of the electromagnetic spectrum that we can see, which is called what? Visible light. Thank you, visible light. Can you see X-rays? You would be awesome. Can you see UV? No, but you can feel it. Butterflies can see UV. They can't see visible light. They can see UV. Fun fact. Yeah. So you can't see gamma rays. So let me tell you, you have some effects from that. So we can only see the special drops of energy that relay a photon with a special wavelength that lies in the visible spectrum. But we can still detect the other wavelengths. So that's what happens when light is put on the electron. They jump up for joy, they're excited, they fall back down from the sugar crash, they put off light or some other form of energy. And that's going to help, that's going to be really involved in the quantum mechanical model. So quantum mechanical model explains how electrons exist and behave, where they live and what they do. It's just now we're not about like the atom at all anymore. The quantum mechanical model, the hot new topic is let's talk about electrons and what they do. And that's basically it. It's going to help us understand pretty much everything, but it's just about the electron. People get their panties in a bunch over their quantum mechanical model. It's just about electrons and everything there's to know about them. Dun, dun, dun. Okay. So it helps us explain a lot of things, and I'll kind of read off some of the stuff as you're writing down. But it helps us explain why metals are reactive in some ways and non-metals are reactive in other ways. It helps us describe colors. It helps us say why some things are uniform cations and what other things are uniform anions. We've just kind of taken all that for granted back in the day, and that whole baby honors chem thing we did. Now we're in big boy chem, and we have to not take it for granted, we have to understand it. So it's going to help us explain a lot about the periodic trends and everything. So this unit should actually call the electron, but then you guys would have been confused. Like, why are we talking about electrons? So you guys can see it's very important to understanding life, and chem is life. Okay, so now we have the electron configurations because now we get to talk about where they live. They live in those special orbitals. Who is this? Who am I describing? What element?
Sulfur.
Vanadium. Thank you, Nick, the sophomore. Okay.
Okay, well, I saw him with confidence like she probably took the one from like,
No.
I didn't even look
Okay, Nick. Thank you. So how do we get from 4s2 to 3d10? Huh? Yeah, but why are we going from 4s to 3d?
Subtract one when you get
Thank
to
you. So when you get on your periodic table, does that have a periodic table? Nope, sure don't. Okay. Periodic table. This is S block. This is P block. This is D block. This is F block. Okay. When you're going across the periodic table, you have that special exception to where n minus 1. What is n? N is the energy level, also known as the principal. Ooh, is it principal? Yeah, principal. Okay. Principal or principal? Principal quantum number. N is the principal quantum number. That just sounds crazy. N is the energy level. It's the period number. It's people get scared and go, principal quantum number, what the heck is this? It's the energy level. So the smallest n is n equals 1, and that's with the first row, hydrogen and helium, that period of the periodic table. So what I'm saying is when we get to D block, you have to do n minus 1 because you'll go like 4s2 and then get to D block and do n minus 1. And then n minus 2 is going to be what happens when you get to F block. Coolio? Okay, so this is following 3 people's rules. Off fall. Does anybody who was in my class remember mine? Okay, off fall, what did I say?
Off fall, low.
Awfully low. Oh, that's close enough. Okay. This is how I remember the cheesy, stupid names and what they mean, why they even matter in the electron configurations. Off fall's principle is you start adding electrons at the lowest energy level. Like, where else would you start? From the middle? Like, where would you put? It logically makes sense, but you have to remember who described that. That's off fall. Off fall said start awfully low. Start at n equals 1. Then you can add electrons up from there. And I'll come right back to this page. The only reason I want to tell you off-fall first is because he has a diagram. And you got to be aware of that. Okay. Off-fall's diagram looks like this. Okay. So you started from the bottom. Now you're here. So you start from here, and you add your electrons up. So from the first energy level, it only has S block, okay? So you got one S. You can fit 2 electrons in there. My electrons are half errors because I'm lazy, okay? There's my 2 electrons. Then you have to jump a long way to get up to the second energy level. This is a very significant energy difference. Okay? That is just, you need to understand that, but the energies between energy level 1 and 2 are very significant. After that, it's pretty short. It's not like I'm going to scroll up and I'll scroll back down to you. Look as I go from S, n equals 2 to n equals 3. Not much of a gap there. As I go to 4, it gets closer and closer and closer and closer and closer and closer and closer. So from n equals 3 to 6, it's almost the same amount of energy change as it was between 1 and 2. So you just need to know that there's an exception. There's a very significant energy difference here. This arrow that goes up, that's called energy. This is called off-fall diagram because it wants you to know that you feel electrons from 1s and then 2s and then 2p. And then 3s, and then 3p, and then 4s, and then 3d, like we were just saying, right? You went from 4s to 3d, and then so forth. But who wants to memorize this? You don't want to memorize this. You want to look at the periodic table. It's your friend. It's going to help you here, okay? So we started off with off-fall's diagram. Off-fall's orbital. Off-fall's rule. Principle. Principle. Okay? The second person to help with designing how electrons fill is Pauli. Pauli exclusion principle. I just remember it as Pauli pairs. Pairs. Not pairs like you need pairs, but pairs of electrons. Okay. So electrons occur in pairs. And that's what you've always drawn with your Lewis dot diagrams. You put them in pairs. Whenever you fill orbitals, you fill them up in pairs. But you don't fill them automatically up in pairs. That's pretty much saying that they are allowed to be a pair, but you can't be triplets and quadruplets and quintuplets and so forth, okay? You can only allow electrons to exist in pairs. Because what happens when we get too many electrons together in a party? They start to explode or repel. I was going to go with the Escalated quickly there. Okay, so they just repel. So if you put too many electrons in one place, they're going to repel, and the atom's going to be very unstable, and then have to go see a counselor and stuff. So, the last one is Hund. Hund's ones. Thank you, Hund's ones rule. Yay, it's stuck. Okay, Hund's ones rule means that when you fill up an orbital, I'm going to draw my orbitals dashes for now. I'm gonna pretend this is the 2p. If all of these are the 2p orbitals, because remember there were 3 of them, right? You fill them up one at a time. Those are electrons. And then if you have more electrons, you can go fill them back up. Like you can follow Pauli's rule and go up to a pair of electrons. But the only reason we have to remember Hund's ones rule is because when you have a not like full block of electrons, you have to fill them up in the correct way. Because they don't like to be near each other if they have a choice. If they have a choice, they will be in separate orbitals because they repel. Okay, so how they are electron configurations or how they are thought to exist in the atom. Central quantum number, period, energy level. Dang, I just said all this stuff. Okay, here's where I want to talk. The SPD, that's telling you the shape or which orbital shape it's existing in, and then the number at the top tells you how many electrons exist there, right? So you kind of already knew that. But I was going to tell you that for a reason. Oh, because I didn't draw an orbital diagram. That's right. I'm erasing this. No, I'm not. I'm just going to scooch it down. Scooch it down. Why do I have this? Why is this marker out? Okay. So if I wanted to draw the orbital diagram for the guy that we have listed here, whoever that was, vanadium. Am I saying that right? Pretty sure. Okay. You have to draw it, right? So we have electron configurations, which are numbers and letters, and we have drawings called orbital diagrams. The diagrams are pictures. So 1s, 2. Good? 2s, 2. Why are these electrons spinning in opposite ways? Right, so they don't bump each other, so they don't create a magnetic field. Okay, they have to spin counterclockwise and clockwise to one another. So one spins up and one spins down. 2p, you have to draw all the orbitals, and then I like to put brackets so that you don't forget they belong together. It goes 1, 1, 1, and then double, double, double. 3s, 2. No. Yeah. Are we on 3? Okay.
Yeah.
3p, 1, 1, 1, double, double, double. 4s, 2. How many do I draw for D? 1, 2, 3, 4, 5. So you have to draw all 5. I don't care if you're using all 5. You have to draw all 5. Because in this case, we're not going to be filling up all 5. We only have 3 electrons in D block, right? So you do 1, 1, 1. You have to leave those other 2 open. So if I asked you, how many unfilled orbitals are in vanadium, you would say? How many unfilled? 5. There are 5 unfilled. How many totally empty? 2. How many unpaired?
3.
I would say if I said unpaired, I'm talking about there's one that doesn't have a pair. I could be more specific with that. You're right. So unfilled 5, empty 2, unfilled 3. Gets wordy, right? Okay. You just have to become familiar with it, and you guys are gonna practice some of that. Don't worry. All right. So check, check. Oh, whenever I say SPDF, those are called orbitals, but they're also termed sublevels because or sublevel or subshells. The only reason that this unit is reading intensive is because you actually have to learn what these words are referring to. That's really it. So if I say a shell, I'm talking about an energy level. So shell 1 is n equals 1, shell 2 is n equals 2, blah, blah, blah. Subshell is in the 3rd energy level. How many subshells are there? In the 3rd energy level. Period. Look at the periodic table. 4. How many different letters would you get associated with 3? 3, yes. I see 3s I hear in front of us. 3p and 3d. Is there such thing as a 3f? No. Where does that come in?
4.
Down here?
Yes.
So that's the 6th. Yeah, that's the 6th row. But as you enter F block, you have to do n-2, so that would be 4f. That would be 5f. Yeah? Okay, so you're good. You said 3, I think. So you said 3 subshells or 3 sublevels that are associated with that. And then valence numbers. This is just a quick read. How do you figure out the valence electrons? Group number. Thank you. So oxygen has how many valences? 6. Fluorine has 7. Calcium has 2. Okay. So I have a lot of words to remind you, okay? The representative elements. The term representative element means the 2 towers of the castle. Okay? The 2 towers of the castle are anything in group A, which are 1A, 2A, 3A, 4A, through 8A. So the representative elements are those that have their general properties that are established. So the alkali metals have a certain set of properties. The alkaline earths have a certain set of properties. The halogens have a certain set of properties. The noble gases have a certain set of properties. So those are representative. They're like representing, you know what I'm saying? They're representing that group. I wish I could be like a chemistry textbook writer. They'd be representing. Okay. The D block has no representatives because they are all very different. Copper is very different than silver, which is very different than gold and iron and manganese. Like, come on, it's purple. So we've got all kinds of different stuff going on. So that's why they're not considered representative groups. They're called the B elements. That's why if you did want to do numbers across the periodic table, there'd be 18 if you included the A and B groups. But we don't, mostly. I did meet somebody who majored in, her name was her PhD. It was very specific. Transition, metal, D block, color chemistry, wavelength chemistry. Just because anything here is very colorful, right? So she measured just specifically in the colors and how they did it and how they moved their electrons. I was like, man, you're cool. Okay. All right, so this is, she's really cool. She's also from England, so she was like, I just was like, mesmerized. So you can speak in the English telling too. British. She was like an AD chemistry teacher too, and I was like, any chemistry. Okay, so anyway, this is going to be the first exception to, I don't think Mr. Neal went over this, but I know I did because you didn't even know it back then because your brains will explode eventually. Anyway, this is a special exception to the electron configuration rules. So you know that copper generally would go blah, 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 3D9, right? Okay. If an element can do a little switcheroo where the electrons exist to become more stable, then it will. And it's not a choice, it just is. This is man-made. Elements didn't make this up. We assign the electron configuration of copper to be this. So when we do some tests and we find out copper doesn't act like this, so this electron configuration will have a specific behavior associated with it, the way the reactivity of it works and everything. So we would expect it to be somewhat reactive because it's just got one, like you could just put one more electron in there and it would be a full D block, and that's very stable. But what we came to realize is that copper is not as reactive as we thought it was, and there must be something different about the way the electrons are arranged. And there is. It's usually going to be with F and D, so F and D blocks, where the elements can start to push their electrons in upper levels or lower levels. So the stability comes in when you have full or half-filled sublevels. So full or half-filled sublevels would mean that if I had 3D10, I would be very stable. So where is that electron going to come from? It comes from making somebody else half-filled. So who here could we make half-filled? 4s. What it does is it's called electron promotion. It's a raise in everything. Benefits everything. You guys are, come on, I'm funny. Okay. My husband watches my videos sometimes and he's like, oh my god, did you literally say that? Okay, so it gets promoted. So it goes blah, 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 4s1, 3d10. And we didn't make this up. We did experiments and we discovered that copper is relatively unreactive. Didn't we know that already? It's really low in the activity series. So we have this general pattern and trend that we associate with the periodic table, but then copper's like, whatever, not mainstream. I'm going to be this. So it's gonna do this electron promotion. This one's half filled, this one's full filled. Everybody's happy. So this is just an exception to the rule. So who else do you think is going to have that exception? Yeah. Chromium. Why chromium? So it would end up being, what is its valence shell? What did I just do? Whoa. What would chromiums end up being? 45s because it's pushing one forward. What else? Anybody else? I heard some. Yeah. Silver and gold. Silver and gold. Okay, good. Because we have this expectation on how they're going to act, and then they don't, and we're okay with that. So these are some examples of what we would expect, and then what actually happens in the lab via experimentation. you don't have to know all these, but you'll notice they're all in the same group, right? Because they're all going over there. You guys can see that, right? It's all of the chromium family because they're all one away from half filled, and it's all the copper family because they're one away from full filled. And they just do one electron promotion from their S block, their most recent S block. So these are a couple of what we expect, and then actually what happens in the lab. Two more than ours then. Oh dang! Sorry guys. Okay, that was taken out of our honors course for like 8 years. Okay, these two words are important words: paramagnetic and diamagnetic. Diamagnetic and paramagnetic, they sound like magnets. They are. It's referring to the ability of the atom or element to have a magnetic field surrounding it or to respond to a magnetic field. I'll let you write down what you need to. Madison, you need me? Yeah or nay? Okay, so paramagnetic. Oh, I thought this was wrong. No. Okay, so if you're going to have a tendency to react to a magnetic field, you have to be somewhat polar. The way that, because polar means, right, polar means like a magnet, you have a positive and a negative end. So a specific atom of an element technically can be polar. But its electrons can be unpaired, meaning one electron spinning clockwise while another one's not counteracting it, spinning counterclockwise, leaving it kind of vulnerable to reacting to a magnetic field. So anything that has unpaired electrons in its orbitals can respond to a magnetic field. So I always say polar kind of atoms are paramagnetic. So give me an example of that. Anything but what? Things in period or in group what? Okay, 18's full. Cheating. Let's go back it up. What else is full? What else is totally paired? Anything in group 2A, right? Because they're all to the S2. Anything in group? Anything in the D10, and anything in P6 or having P6 electron configuration. Does that make sense? So everything else is paramagnetic. Those that we just said were full, they're diamagnetic. So diamagnetic means that they will not respond to a magnetic field. So I would always think diamagnetic don't. Just don't. This is how I teach myself chemistry. Okay, they just don't. They're paired. They're doubled. I don't know what you want to say, but they just don't. They have a full doubled up pairing system. So nobody's free to go play with the magnetic field. Nobody's going to respond to the magnetic field. So sometimes you'll just have to identify things that are diamagnetic or things that are paramagnetic. Don't get too caught up on this. Paramagnetic, they're polar. They're going to pool. They're going to be affected because they don't have something paired with them. Diamagnetic don't, because they have doubles everywhere. So no tendency to be attracted to an electronic or a magnetic field because electrons are paired. Ready, Freddy's. Okay. Oh, so these, what does paramagnetic mean again? Magnetic? So they do respond to magnetic field, right? Why is that? Because this guy, 4s1 is unpaired. Even though the end is paired, even though the exception occurred, it still is going to respond to magnetic field. Okay, grounded and excited state. I kind of explained this already. Excited state, the photon hits, it jumps, it goes woo, and releases the energy. The photon comes off. Okay, that's called excited state versus ground state, where they're just down. They're grounded. They're locked in their room, and mom's not letting them play PlayStation or something. Okay, they're not going anywhere. They're near home. They're near the nucleus. Very attracted to the nucleus means that they're very stable. Very stable means that they're not likely to be attained and brought out to chemical reactions. More pictures of that. Oh, I didn't do ions. Give me the electron configuration of calcium ion. 1s2, I got you. Continue. 2s2. 3p6, what? 4. I said a calcium ion. Oh, stop there. You don't even tell me about it. So that's it, right? So this is called, okay, this is the electron configuration of who, if it were just the electron configuration? I believe you, yeah, argon, okay. So this is the electron configuration of argon and the electron configuration of calcium ion. So they are called, when the calcium ion forms, isoelectric. Why iso? Not an isotope. Isosceles triangle means same sides, right? Okay, they have the same electron configuration. So isoelectric means same electron configuration. But no two elements can have the same electron configuration, so it must be one has lost or gained electrons to look like somebody else. Why in the world would you want to look like somebody else? So your energy levels are full and you're stable, right? Okay. So calcium is relatively reactive because it's got 2 extra electrons just hanging out doing nothing. And then calcium ion is very stable, which is why calcium likes to avoid calcium ion. So of those, we are going to say 4s2, it's the 4s2 electrons that are lost. Okay, electromagnetic spectrum, you need to know the order. And I can't remember, I think I told you guys this in honors, but maybe not. Here's how you remember the order of the electromagnetic spectrum. You can see it goes from really tiny wavelengths to really long wavelengths. Really tiny will make you the Hulk, really long will make you hear music, the radio waves. So I'm going to tell you my order and then I'll come back up here. Gonna X, your voice in my radio. I was like, what did I say? Gonna is gamma. I made this up and I was really embarrassed to tell people, then I was like, just embrace it, it's okay. Okay, gonna X, so what's X stand for? X-ray. Your UV, voice, visible. Okay, infrared, IR, infrared is IR. Microwaves, radio.
Why'd you just say country all of a sudden?
I just tried. And you when I can. Okay, so gonna extra voice on my radio means like you're gonna break up with somebody because you're not gonna listen to them. Yeah. So anyway, small wavelength, and then X-ray, and then UV, and then IR, and then radio. Visible. It's an I. Let's see you. Visible. It says visible. Okay, so that's an order of increasing wavelength. Thumbs up when you're done here. EMS, this is every wave practically that we know of is all just straight up energy, but we're going to come to find that energy is more than energy. Dun, dun, dun. Okay, which wave of light, which color of light is most energetic? Red is lame. Purple. Ultraviolet. Violet, visible is, so you can see I have it written as here, because violet is on the UV side, ultraviolet, and red is on the infrared side because it's red. This one, 400, I know, right? They didn't try to trick us up. Yeah. It's just UV is ultraviolet, it's on the ultra side of violet, infrared, it's on the inside of red. So, anyway, UV, is very energetic. It will cause cancer in your cells, right? It will mutate your DNA. Very energetic. So high energy because it's moving really fast and it's got really small wavelengths, so it can actually penetrate your atoms, your carbon and hydrogen and oxygen and everything that
sounds bad,
right? But radio waves, the light is not really penetrating your cells right now, but UV can when you walk outside. Now, microwaves are fairly large, right? So have I told you guys this before, the little screen on the microwave? Maybe I told you. So there's a mesh screen on the microwave that you can't. It makes it so you can't see your food. Okay, that's for protection. It's because the microwaves will come out and attack you, but they can't squeeze through that little hole. They're too large to fit through the mesh hole. So the mesh is protecting you from radiation poisoning. Yeah. Yeah. Don't do that experiment. I don't know. Because you guys know microwaves, all they do is they hit the water molecules in your food and they make the water molecules vibrate really, really quickly. And as they vibrate really, really quickly, it's increasing the kinetic energy, which causes temperature to increase. So just the only reason the microwave works is because it causes your water molecules to get real excited and move
Before you
around.
put water on stuff. Before you put it in the microwave.
Yeah, that's why you put some water on those little noodles, or cup of noodles, or ramen. Announcements. Okay, so anyway, if you, which are like 90 or whatever, 70, what percentage are we of water? 75. You're mostly water. The microwave would make you blow up. Okay. So, like you would melt. You would get so like just energized with kinetic energy. You would melt. Tara, I'm gonna dream about that. Huh? Yeah.
Tara is more
Okay.
Tara likes videos of people being in the
Come back to me. You're killing the fish now. Come back. Okay. Let's go into calculations. These are my math people, right? Okay. Calculations. So, two equations you need to know. It's okay. We're not going to finish today, but I'm having fun with it. This is working. C is equal to lambda by times frequency. C is the speed of light, 3.00 times 10 to the 8 meters per second. Lambda is wavelength. Commonly it's given in nanometers. Huh? Oh, sorry. Commonly it's given in nanometers. So this little broom looking upside down Y, that's a lambda, like that. Greek of some sort. I can't remember the letter. I think it's got to be L. Lambda? L? Okay. That makes sense. Okay. So this is the speed of light. All light travels at that speed. We generally say all electromagnetic waves, everything travels at that speed. And we are going to stick with that, okay? It might be a teeny bit of a lag, but it's good. So that's the speed of light. I will give you that number. No worries, but you'll probably accidentally memorize it. It's cool. It's generally given to you in nanometers, though, but you'll see this has meters in it. So what do you have to do first before you can use meters? All right, so if I give you 485 nanometers, you multiply by 1 meter over nanos 10 to the 9th, because it's 9 zeros away, nanometers. Nanometers cancel out, so that's 4.85 times 10 to the negative 7 meters. Okay, yeah. Because the speed of light is a constant, you're not allowed to change that. That's a universal constant, so don't change it.
Why don't they just change it to them?
Because for us to write, because that's been established for probably 150 years, so I don't have that kind of power. But this right here it's hard to visualize that this is in the visible wavelength of light. Visible is between 400 nanometers and 700 nanometers. So if I see that I'm given 485, I know that's blue-green. If I'm giving you 700, I know that's red. It's more of an association, it's invisible light than anything else. Okay, so the frequency that we're given is usually established in hertz, but those hurt because you don't really know those units. That one wasn't very good. But this is going to be how they're generally given to you. Seconds to -1, which just means per second. And that helps you, I'm going to type this in meters right here. That helps you see if wavelength is in meters and hertz is in per second, then meters per second is how you get speed of light per second, or meters per second. So anyway, the frequency is just the definition of that, cycles per time, and so seconds is what we choose. And the wavelength, if this is is this a sine wave? Sine? Yes? Because this is my axis? Okay. So from here to the next crest, that is the wavelength. It's the length of the wave. It's not hard. Okay. And then, I need to show you this. This is the combined, no, this is not the combined. This is me solving for wavelength. I don't know why that's there. I'll tell you more in a second. Yeah, all electromagnetic waves, EMS, travel at that same constant speed, supposedly. Hard to test sometimes, though. Moving on. Okay, so Einstein. Okay, so Einstein, you know, he's credited with E equals MC squared. What do you think each of these things stand for? Energy, mass, speed of light. So, what is he saying about mass and energy?
That they are inversely related.
They're directly related to what he's actually saying. Because as this increases, this must increase because the speed of light is a constant, right? Okay. So mass. This little robot guy. He's saying that this mass has energy. And I mean, I could catch it on fire and show that, but no, it's not. It's not like talking about thermal energy. It's talking about energy of the wave. So this gets us into something called the particle wave duality. Because before this, we just said waves, energy. They move at the speed of light, and they have a wavelength and a frequency. Energy. If I had said radio wave, would you have said that contained matter? No. If I said microwave, would you have said that contains matter or has mass? No. You would have said no. Anything that's energy, you can't mass that. You can't put that on a scale and mass microwaves or light. You can't mass that. So what they said was energy was energy and mass or matter was matter. There was no relation between the two. There was no correlation. We couldn't really relate them. But then what started to happen was this. We started to get more knowledge about the atom. We started saying this energy, this light that we're shining on the atoms, it's causing something to occur. We're causing matter to change. Matter being electrons, which, yeah, granted, they're tiny. They supposedly have a negligible mass, but we know they have a tiny amount of mass. Because they are something. They're not energy, they're something. I could pick up an electron if I could. Right? So what they're saying is that if energy has an effect on matter, to cause matter to change in this way, where it released energy, that means they're related. So then Bohr, de Broglie, Planck's constant, Planck, and a bunch of people came together and we said, okay, we need to figure out that relation. The relation is Einstein's equation and de Broglie's equation, which is in just a second, okay? So anyway, this is really important in not only showing the relationship between matter and energy, but it's also important because that's how we get nuclear energy. So the mass defect in nuclear reactions, when things are decaying, when matter is decaying, it releases a lot of energy, especially if you split the nucleus. But if you mass the before and after of a nuclear reaction, there's mass missing. So it's like, oh my gosh, law of conservation of matter is a lie, right? But no, they realized the matter that was missing was because it transitioned to energy. Normally, we would say no. Matter that was present before a reaction is also present after the reaction. It's just rearranged. But so that also, it just goes into more detail about the way nuclear reactions occur. Okay, so quanta and photons are going to be two words we use a lot. And then we realize that light is just a quantum of energy, and it's related to the frequency of the traveling wave. So if this photon was moving really, really, really quickly, it would be delivering a bunch of energy to this atom. A bunch of energy to this atom would also release a bunch of energy once it came back down to an excited state. And so what they said was like, okay, normally more energy delivered means that the wavelength is going to be having more energy and having a higher frequency. But they realized it was in very specific quantities. It wasn't just any old energy was released, like every energy known to man. It was very specific in the multiple that it was achieved at. And that's where Planck's constant comes in. And I'm going to scroll all the way down right here. So energy that we're talking about related to the frequency of that wave was in specific quantities, was in specific multiples, and multiples of this thing called H. H is Planck's constant. So at this point, you could find out the energy of a traveling wave. We used to only be able to get the wavelength and the frequency of the traveling wave, but now we could get the energy of the traveling wave. And then that was very important because that's all Bohr's model is. It's just a bunch of energy levels, and we want to know the energy of each level and the stuff that changed in between. He did that by studying hot glowing solids. That's not really that important, but it's there, so I'll read that off. Yeah.
So if Bohr's model is like not correct.
It's correct for hydrogen. I'll give him that. Okay.
So how come we're like using
It's very, very good in understanding how energy is related to matter and light. That's the only reason, really.
Is there an extra photon right there, or is that,
One photon. That says photon.
okay, but it says per photon?
Yeah, so for one photon. I don't know why I wrote them twice, but I did. Okay, so this is the energy. So this is E of a photon, which is a packet of energy, is equal to Planck's constant times the frequency of that wave, whatever the wave is. And a lot of times when we say photons, we are dealing with light here. We're trying to stay in that visible spectrum because who cares about gamma rays, right? So we're really concerned about light in this case. Huh? Yeah. Horrible. Okay, let's do one more thing. We got 15 minutes left. So back up here to the quantum theory, Einstein and the intertangled matter and energy kind of debate they're having. They started to actually put a name to that debate. Do I need to scroll back down? Anybody? Sorry. They started to put a name to that debate called the particle-wave duality, or particle-wave nature of matter. So the two together make this thing, which means matter and energy are Jekyll and Hyde, right? They have properties of both of those identities. Particle means that you are a particle. You have mass and you have volume. But even this lion, who's just lying here, even this lion, okay, has wave properties to it. You can't see it, but it is vibrating. I'm not making it. It's vibrating because it's made of matter. Matter is not static. Matter, this solid, has little bitty vibrations related to it. And those vibrations, if I let them move, would be in a wave. Okay? So matter does have wave-like properties to it as well. So that's what I mean by wave. I mean has a wavelength and frequency associated with it. Yeah.
Is that what we're vibrating?
Yeah.
Is that why we're technically never touching anything?
Yes. Because we repel each other. We're not touching you. Oh, sorry. I'm actually hovering right now.
Oh, that's like field difference.
Because we have electrical stimuli that tell us we feel things.
We don't have things. I specifically that I'm not.
This matter that's below me is holding me up right now because it's repelling me. The nuclei between the shoes and the floor.
So we're like hovering.
I hover at all times.
Fly.
Look. Oh no, I can't do that. I was going to jump up and do like that. Probably hit my face. Yeah, we're hovering. It's just it feels like we're touching things because our nerves are detecting some sort of pressure, and I mean, taking that. You got the electrical stimulus in your brain perceives it as that.
It's like when you fall and break bones.
That's a force. That's just a force debate. You've created a force that was stronger than the force holding your bones together.
Okay.
The force of the floor that was repelling you to get back up. The floor is just trying to help you get back up, and it stopped you from going through to the next room below us. I mean, it was trying to help. You shouldn't have followed. Okay. So anyway, as we bring together two thoughts: Einstein's equation and the other E equation, which was what? E equals hv. You can come to this new equation, which is called de Broglie. I don't know how to say his name. De Broglie. His equation, because what we do is we can rearrange. Oh, I'm sorry, I forgot this one. Speed of light. Because what we can do is we can bring these two equations together. How would one do that?
Put the V on either side and then the wavelength together.
What? Oh, I heard like
Solve for V.
solve for V. So V, which is frequency, is equal to C over, over lambda. Plug that in there. Someone plug that in there. Yeah. E is equal to H times C. Sorry, this thing has reset 3 times today. It's freaking out on me. Over lambda. And then I'm going to rearrange. I can't put C. I can't do C just yet. Hold on. I've got to rearrange this. So I got to put energy. This thing, wavelength is equal to hc over energy. I just switched these two, right? Okay, now energy is equal to mc squared HC over MC squared. What are the C's cancels, right?
Yeah.
So H is equal to, wavelength is equal to H over MC. Then, you don't know this. You may, I don't know. I don't want to belittle you. Joule seconds is what H is measured in. Mass in the SI system is in kilograms. C meters per second. How in the world do we get length?
You cancel out your second.
Okay, so you can cancel out some seconds, okay?
And then you can turn kilojoules to
No, this is a kilogram and this is a kilojoule, so they're not related, right?
okay.
I'm not going to go into the details, but joule is equal to a Newton meter. A Newton is a unit of force in physics. A Newton is equal to a kilogram per meter second squared. So that's how we get meters in here, because a joule is equal to a Newton meter. And then we just interchange this stuff. And then we get this magical equation. Okay? This is velocity, though.
So through witchcraft, you
Witchcraft, yes. I prefer alchemy, not witchcraft. That's cool. So anyway, that's the Broglie's equation. It does take a lot of things to put it together. We don't have to know how to put it together. We just have to understand what goes in here. Mass in kilograms, velocity, which would be measured as speed, joule seconds is our H Planck's constant, and wavelength is how you calculate that. Yeah.
So, BB theory, is that the one that you rise from the moon?
Both of them are written as me. Yeah.
So you rise from
So the velocity and frequency for chemists, we really think they're the same physics, so you can totally separate them. Okay, so I'll do this problem tomorrow. We'll do what is the wavelength tomorrow? This is a tomorrow, okay? And then, because yeah, I tell you velocity on that one, by the way. Hold on, I'll tell you Heisenberg's tomorrow too. Told you about the photoelectric effect. Bohr's model. Okay, I'll have to do this tomorrow. We might be lecturing a lot of tomorrow, okay? I have to catch you up on this.
I might actually do too. I like.
Especially when I tell you all my
I would
jokes.
say just learn things to not test on.
Maybe for a month? Yeah, two pencils for a month.
We're not gonna know what we say.
Yeah, we will.
I know it.
Okay. So I have to stop talking for a minute, but I'm back now. I'll tell you about, let me just finish up these last two slides and then we'll be done. We'll do the EMS calculations more tomorrow, but I do want to try this. What is the wavelength given the mass of an electron is that, oh, that's the mass of an electron. I knew I had a 1 and 9, but dyslexia. And then velocity is this. How do you want to solve for that? We are doing this. So I'm going to put that like that. Look at it real fast. Okay. Wavelength is equal to what? Mass times velocity, right? And then H is 6.626 times 10 to the negative 34 joule seconds. Mass is given as this, 9.019 times 10 to the negative 31 kilograms. I always want to say joules. And then velocity, meters per second. Okay, so then I know everything's not going to cancel. You are going to have to let go of that. I know I've hammered units with you, but do not try to cancel these units because that means you would have to convert to joules, Newton meters, Newton stuff. So ignore the transition of the units, but that's going to give you wavelength, okay? And then assuming we get wavelength, I'm not going to finish that calculation. Wait for me. Assuming we get wavelength, how would I get frequency? C is equal to wavelength times frequency, so we plug in the wavelength right here. So we would do V, or nu right here, this is frequency, is equal to C over lambda. Are mathematically minded people okay with this? Yeah.
So, do we like distinguish between the two V's, or do we know based on the
For chemists, we're going to call them the same. But just understand that you will eventually separate them when you get to physics. Okay, I'll have to tell you Mr. McNeil's joke. Heisenberg and Schrödinger were going down the highway really fast I know. Gosh. And they were going really fast. They got pulled over, so the cop goes, gentlemen, do you know how fast you're going? They said, no. He was like, you guys are going 108 miles an hour. They're like, oh my gosh, now we're lost. Because Heisenberg says you cannot know both the position and the speed of an electron. You can know one or the other, but the more you know about the location, the less you know about the speed. The more you know about the speed, the less you know about the electron. So as soon as the police officer was like, man, guys, you're going 108, they're like, oh, no, we're lost. And they didn't know where they were. Yeah. Just Schrodinger part, because he talks about this thing called, because him and Heisenberg worked really closely together, because they were a part of like a big group of 6 or 7 scientists that did the wave mechanical model or quantum mechanical model, and they came up with this thing called wave function. And I read that as the devil symbol.
Yeah.
Because the wave functions, if you want to read about it in your free time, is a calculus awesome disaster. It's crazy, okay? So you guys can read into that on your own. And the last thing about this model is you guys can read that. You read that. Read it. And I'll act it out. Okay, energy is transferred. Pass it.
No, I don't. It's on the floor.
Oh my gosh. It's off balls. So, photoelectric effect is that when photons, which is energy, hit the matter can eject electrons. And we have experienced this when we are shocked by a grocery store cart in Walmart. Yeah? Light hits the metal ejects electrons, you feel it as a shock. We also utilize this, right? We also utilize this by solar cells. So Hansel, who made a solar cell phone charger, can put his little cell phone charger out in the sun, which is photons, hits the metal. It's silicon. I mean, it's a metalloid. I don't get it. This is a wafer of silicon. This is one crystal. One crystal of Si, okay? And what happens is it's a metal-ish, metal. And when the light hits it, there are a lot of electrons that are free to move. They move really, really quickly. And when they move really quickly, we capture them in a galvanic cell. Remember how we capture electrons? Make electricity. But we're getting it from the sun because the sun is providing us with photons for free. Right? So that's that. We already know what the photoelectric effect is. We just didn't know it was called the photoelectric effect. Okay. Oh, and then, sorry, the last part of this is, if I really, really, really wanted to affect electrons more, would I send more energy into it, or would I send less energy into it? More. If you want that electron to jump out of the atom, to jump from n equals 1 to n equals infinity, you would have to hit it with a really, really, really high energy photon. What color would that be? Purple. Red is lame. Hey, purple is good to go. All right, so purple is ultraviolet, really high energy. It's going to deliver a lot of energy to the atom, and the atom can then emit or eject electrons. And then as they eject electrons, we capture it and harvest it for energy, right? Because electrons is just a bunch of electricity is just a bunch of electrons. And then as you, so what you can do is you can change up the wavelength of light, or you can increase the intensity of the light. The sun has high intensity, but that little laser has low intensity. So you can change up your ability to eject electrons based on the frequency, the wavelength, frequency, they're indirectly related, and or the intensity of light. And that's what happens. So sometimes they'll say here, HV, but we know what that means, energy, from a photon. Okay. That's all I'm going to do right now. What I might do is teach this through a lab. So you have to try your homework, because I think you can do most of it. Page 337 on the packet I gave you. So under the light and matter, so it's 39 through 60, 69. Oh, you know what? You will only be able to go through 55. I hope you're listening. Yeah. You're only going to be going from 39 to 55. We have not talked about quantum. So you have to do this, and what I would recommend is that if you are lacking knowledge from something we talked about today, read from do extra questions from page 77 in your textbook. But you can peruse through your textbook really easily and pick up the things you're like, oh yeah, I need to learn more about this. I'm not going to assign more questions and more reading because this is something that is very individual, the amount of practice you need. Okay, dokie? Yeah.
How do you do the energy from one?
Ooh, yeah, I'm sorry. The one with the exact electron transitions, sorry, I didn't look at that very closely. I just looked at the ones I needed to do. You won't be able to do 452 or 55. You have very little homework. Okay, so you won't be able to, because I'm not going to teach you the Reinberg equation in 1 minute. Reinberg equation, you're doing like 1 or 2 problems, and you should go back through these. You're welcome.
Miss Summer, I was looking for a periodic table online, and I came across the periodic table of your period.
Oh, like, hold on, let me stop videoing for a second.
What is that? It's a periodic table of your